A very good morning, and you're welcome to today's Signpost webinar. We hope you're keeping safe and well wherever you're joining us from today. Today we'll be discussing how farmers can reduce their climate emissions without compromising on profitability. Ireland's Climate Action Plan has set a target of reducing emissions from agriculture by 25% by 2030. And this translates to a reduction of 5.75 million tonnes of greenhouse gas emissions. So delivering this reduction in emissions will require a significant transformation in Ireland's agriculture and food production system. We do know that. And today we'll be discussing how one of Teagasc's flagship research farms is achieving a significant reduction in greenhouse gas emissions without compromising on profitability. And we're delighted to be joined by Owen Cashman, who's a PhD student working down in Solohead in County Tipperary on a research farm with Dr. James Humphreys and colleagues in delivering and developing blueprints for Irish dairy farmers, how they can reduce their emissions. Owen, you're very welcome.
Thanks, Mark. Thanks for having me on. Delighted.
Great to have you on board. We have Meabh O'Hagan as well on standby. Meabh, you're going to help us out with questions throughout this morning's session. So a reminder to everybody that please do use the Q&A tab at the bottom of your screen, and we'd be delighted to put those questions to Owen later on. Owen, maybe you could tell us a little bit about your own background and the work you're doing in Solohead.
Yeah, so I'm a final year PhD student under the supervision of, as you said, Dr. James Humphreys, who's the Principal Research Officer at Solohead, and Dr. Imelda Casey within the Land Sciences Department of the Southeast Technological University. I'm in the final year of the PhD study. I come from a farming background myself and studied agricultural science in UCD, and then joined this project just 3.5 years ago now. So.
Very good. So you're going to tell us all about the project. So I'm not even going to start asking you questions about the project and steal your thunder.
No worries.
So what I might ask you to do is if you could share your screen with us, Owen, and we'll get straight into the presentation, and remind everybody that today's session is being recorded and will be available on the Teagasc YouTube channel in the next coming days, as well as Owen's presentation. And you can listen back as a podcast on all of the popular podcast platforms. So I think Owen will get straight into it, and we will chat to you after the presentation, and looking forward to lots of questions coming through from our audience this morning.
Great, thanks, Mark. So I suppose as we have established already, the presentation is going to be focused on lowering the carbon and ammonia footprints of milk production at Solohead Research Farm. And just to jump straight into a small bit of background as to the motivation behind the project, as Mark has outlined already, we have a significant profile coming from agriculture in terms of the greenhouse gas emissions, with 38% of the overall national emissions in Ireland coming from agriculture. We're on the back of a recent period of intensification from dairy farms in Ireland. We've seen a period of rising emissions, in particular in relation to post-quota abolition on dairy farms. This has given us a target of a 25% reduction in the greenhouse gas emissions from agriculture under the Climate Action Plan to be reached by 2030. And as well as that, within the umbrella of the project, 99% of ammonia emissions are produced from agriculture also. So within the context of that, there was key objectives established by the project. The first one was to lower greenhouse gas and ammonia emissions on pasture-based production systems using what I'm going to describe throughout the presentation as a best practices approach to lowering emissions. The other objective was to simultaneously maintain profitability. Within this framework, there was also sub-objectives to develop nitrous oxide emissions factors for biologically fixed nitrogen in association with clover, and to determine an ammonia emissions factor for biologically fixed nitrogen in association with clover also. And I'll explain that as I work through the presentation. So when we talk about lowering the carbon footprint of intensive dairy farms in Ireland, this slide is representative of the types of emissions profiles that we are looking at. So this slide is representative of a subset of dairy farms used in a study published in the Journal of Cleaner Production by Marion Sorley in 2023. These Irish commercial dairy farms had an average stocking rate of 2.42 livestock units per hectare, fertilizer nitrogen input of 272 kilos per hectare, and most importantly, a carbon footprint averaging of 1.18 kilos of carbon dioxide equivalent per kilo of fat protein corrected milk. So as such, this was established as a baseline for the present study in terms of how we were going to achieve emissions reductions. We can see that the vast majority of emissions are coming from feed digestion from cows and their replacements in terms of enteric fermentation in the form of methane. But secondary to that, and probably most importantly in the context of this study, 19% of the emissions were coming from fertilizer nitrogen. So to achieve the objectives of the overall project, there was a number of systems experiments that Solohead categorized and grouped into three system categories that I'm going to refer to throughout the presentation. The first one is abbreviated as INT and is representative of intensive conventional practices over the last decade or so on Irish dairy farms. The second system is a system ran over many years at Solohead, which is categorized as a best practices to lowering emissions with some application of fertilizer nitrogen in the spring at Solohead. And the more recent data within the study is a best practices without the use of fertilizer nitrogen across the system, the experimental system. So you can see across 5 different experiments within 2011 and 2012 in the first experiment, the intensive conventional system was compared with the best practices system with fertilizer nitrogen. The same comparison was made in the second experiment in 2017 and 18. In 2019, the addition of the best practices without fertilizer nitrogen system occurred. And then in the fourth experiment across 2020 and 2021, the 3 systems were compared simultaneously, with the final experiment just comparing the best practices with and without fertilizer nitrogen. So just to, I suppose, explain the characteristics of each of the system categories, the intensive conventional system has a nitrogen fertilizer input of between 250 to 280 kilos of fertilizer nitrogen across the duration of the experiment. The nitrogen fertilizer type on the system was in the form of urea and calcium ammonium nitrate. So across the first 2 rounds of application in the springtime, nitrogen fertilizer was spread as urea, with the remainder throughout the growing season spread as calcium ammonium nitrate. The clover contents on this system were the lowest of the 3 categories at 10%, and slurry application was spread using the conventional splash plate method of application. So the best practices with fertilizer nitrogen had a lower fertilizer nitrogen input ranging between 50 and 150 kilos of fertilizer nitrogen per hectare. The nitrogen fertilizer within the system was spread in the springtime only, and in the first experiment across 2011 and 2012 was spread as urea, with the remainder of the experimental years from 2017 onwards adopting the use of protected urea. So the clover contents on the system were higher at 23%, and slurry application was spread in the form of low emission using the trailing shoe. So the best practices without fertilizer nitrogen then had minimal fertilizer nitrogen input, less than 5 kilos per hectare across the experimental system, which just represents a small amount of nitrogen fertilizer being spread on reseeded swards to help sward establishment. Concomitantly, clover contents on the system were highest at 29%. And again, slurry application was in the form of low emission using the trailing shoe. So within the context of attempting to lower the emissions from the farm systems, there was an additional practice of using high genetic merit dairy cows using the economic breeding index across within the experimental data set. So across the first experiment, there was no difference in the EBI between the 2 systems compared. However, between 2017 and 2021, there was higher EBI cows placed on the systems that were adopting best practices. So in 2017 and 18, the best practices with fertilizer nitrogen had a higher EBI, and the best practices without fertilizer nitrogen from 2019 to 2021 had higher EBI cows placed on the system, with no difference in the final experiment in 2022. So getting to the first metric of how the systems compared to each other to look at the overall pasture production in terms of tons of dry matter per hectare, we can see that when we compare the systems between individual years across the first experiment in 2011, the intensive conventional practices system achieved a higher herbage production by a ton compared to the best practices with fertilizer nitrogen. In 2012, there was no significant difference, and combined across years, there was no difference between the 2 systems within the first experiment. As we move through the rest of the experimental systems, comparing between years, we can see that there was no significant differences in overall herbage production. And averaged across the whole data set, or combined across the whole data set, excuse me, there is no significant difference in overall herbage production. It is noteworthy to notice that 2012 and 2018 on both the intensive system and the best practices with fertilizer nitrogen were systems with or were years with below average herbage production due to very wet conditions in the summer of 2012 and drought conditions in the summer of 2018. So there's a greater variation within the 7 years included on the intensive and the best practices with nitrogen compared to the best practices without fertilizer nitrogen. So we can say that across a number of years of experimental data, we're achieving parity in terms of the pasture production in terms of tons of dry matter per hectare. And this is across a range of different fertilizer nitrogen inputs. And there's a clear reason for this, and it's in terms of the level of biologically fixed nitrogen associated with clover being achieved on the best practices on the best practices systems, respectively. So we can see this graph simply shows that there's a strong correlation between nitrogen fixation associated with clover and the level of fertilizer nitrogen input across the systems, with the lowest levels of fixation occurring on the intensive conventional systems, the best practices nitrogen being intermediate, and the best practices without fertilizer nitrogen achieving levels of fixation between around 220 and 260 kilos of nitrogen fixed per hectare. We can say that excluding an outlier here in 2012, that 94% of the variation in biologically fixed nitrogen across the systems is directly related to the fertilizer nitrogen input across the systems. So when we look at how the systems performed in terms of milk production per cow, so the milk production here is expressed in kilos of fat protein corrected milk, we can see no difference across the first experiment. Within the other experiments, there was differences in terms of the best practices systems in 2017 and 2020 achieving higher kilos of fat protein corrected milk. However, combined across the data set, there was no significant difference in terms of milk production per cow across the 3 system categories. So essentially, we've established that we have reductions in terms of we have achieved parity in terms of the production across the 3 system categories for pasture production and milk production per cow at very similar, at the same stocking densities. So the next part of the presentation is going to be focused on looking at the greenhouse gas emissions from the 3 systems, initially focusing on the carbon footprints. And the first element to do that is to look at one of the sub-objectives that I explained at the beginning of the experiment in terms of determining an emissions factor for nitrous oxide N from biologically fixed nitrogen. So currently, within the inventories for calculating carbon footprints of milk production systems, there is no emissions associated with the fixing of nitrogen from clover. And this is down to a lack of evidence to suggest that there is any emissions coming from this nitrogen source. So to qualify and quantify this question, we set up experimental systems at Solohead to measure the emissions coming from biologically fixed nitrogen associated with clover. So within the last couple of years at Solohead, there was a grassland systems plot trial with 3 different treatments. The first treatment was a perennial ryegrass sward with no inputs of fertilizer nitrogen. The second experimental treatment was a white clover sward receiving no inputs of fertilizer nitrogen. This was to establish the emissions coming from biologically fixed nitrogen relative to the background emissions from mineralization on the first treatment. And the third treatment was a fertilized grass sward receiving 250 kilos of calcium ammoniate nitrate N per hectare. This experiment was combined with previous work done at Solohead to achieve the same goal of measuring emissions from biologically fixed nitrogen, conducted by Dejan Lee and William Burchell, which had the same 2 experimental treatments in terms of measuring fixation, with a slightly lower level of nitrogen fertilizer input on the treatment receiving calcium ammoniate nitrate fertilizer. So in terms of the most recent experimental data, we can see that in terms of annual nitrous oxide emissions, so the kilos of nitrous oxide N we're losing from being generated from the 3 treatments, there's no significant difference in emissions coming from the sward receiving no inputs of fertilizer nitrogen or no inputs from biologically fixed nitrogen compared to the system achieving nitrogen inputs from biologically fixed nitrogen. We can see that there's significantly increased emissions from nitrous oxide N coming from the system receiving fertilizer N. And what this can establish is that the nitrous oxide emissions factor for biologically fixed nitrogen is clearly 0. Combining that with the previous data from the other experiment from 2009 to 2013, we can see a very similar result where we have no emissions coming from biologically fixed nitrogen between the first two treatments, with higher emissions coming from the fertilized nitrogen sward. So we have a good, robust data set giving us a clear result that there is no emissions associated with biologically fixed nitrogen. What this data set also allowed us to do was create a site-specific emissions factor for the application of calcium ammonium nitrate fertilizer. So when we look at the emissions lost in terms of nitrous oxide N on the two treatments receiving fertilizer nitrogen, the losses per kilo of nitrogen spread are 3.12% nitrous oxide N lost. So where this becomes relevant is in terms of the emissions factors used for calculating the carbon footprints in terms of a life cycle assessment. So the National Inventory Framework at the moment, as I said, has an emissions factor for biologically fixed nitrogen of 0, an emissions factor for calcium ammonium nitrate of 1.49%, 0.25% for urea, and 0.4% for protected urea. So we can see that within the framework of this experiment, there was a drainage impeded soil measured as well, which had a higher emissions factor for calcium ammonium nitrate at 2.74%, which is in line with the experimental data that I just presented in the last number of slides, giving us the site-specific emissions factor for calcium ammonium nitrate. But I suppose most importantly, in the context of reducing emissions within the experimental systems, the important thing to note is that there is no emissions coming from the inputs of nitrogen from biologically fixed nitrogen associated with clover. So we've determined the emissions factors for nitrous oxide to be used across the three systems. So the next step is to calculate the carbon footprints using a life cycle assessment. So I'm going to present the results using the two sets of nitrous oxide emissions factors I presented in the previous slide. So just to give a bit of background into the life cycle assessment model used, it's a model that was used in a recent publication by Marion Sorley in the Journal of Cleaner Production. It's a full cradle to farm gate life cycle assessment, meaning that it takes into account emissions from the upstream processes to do with fertilizer production and transport, as well as other upstream processes to do with the production and imports of concentrate feed. It takes into account emissions from on-farm activity up to the point where milk or meat is sold off the farm. So we took the production data that I presented from both the intensive and the best practices systems at Solohead, and we modeled them on the basis of a 50-hectare farm. We then expanded this area by 9 hectares to include the rearing of replacement heifers under the same agronomic management as the 3 system categories. So as I said, I'm going to present the results using both the National Inventory Emissions Factor Framework and the site-specific emissions factor for nitrous oxide that we've measured at Solohead. So the average farm profiles, as I said, come in with a land area of 59 hectare. The number of cows is very similar across the 3 systems, reflective of the average stocking rates of where the data set was, of the average data set of the systems. The replacement rate for each herd was calculated at 18% and was not different across the systems. The kilos of fat protein corrected milk across the systems is very similar due to the similar output in terms of milk production per cow across the systems. And averaged across the data set, the levels of fertilizer nitrogen input is 265, 100, and less than 5 kilos of nitrogen per hectare for each system respectively. So when we calculate the carbon footprints in terms of the national inventory emissions factors for nitrous oxide, we can see that the greenhouse gas emissions per kilo of fat protein corrected milk are highest on the intensive conventional system at 0.9 kilos, dropping down to 0.76 and 0.69 respectively for the best practices systems. So a similar level of reduction is seen on a per hectare basis. So the greenhouse gas emissions in tons of carbon dioxide per hectare are 12.9, dropping down to 10.11 and 10.2 on the best practices systems respectively. So essentially what this has allowed us to achieve, the best practices zero system has achieved a 23% and a 21% reduction in terms of the greenhouse gas emissions per kilo of fat protein corrected milk and per hectare respectively relative to the intensive conventional system. So to attempt to establish where we're getting the majority of emissions reductions, we looked at the relationship between nitrogen fertilizer input and the carbon footprint per kilo of fat protein corrected milk. You can see by the trend line that there's a strong correlation between the inputs of fertilizer nitrogen and the carbon footprints across the 3 systems, with around 84% of the variation in the carbon footprints of the of the carbon footprints of the systems being directly related to fertilizer nitrogen input, the remainder of the differences being achieved by the other practices adopted on the systems. So again, just to reflect that point in terms of the greenhouse gas emissions per hectare, this graph here shows the clear difference in terms of tons of carbon dioxide equivalent per hectare across the three systems. And then it's broken down into the three main contributing greenhouse gases across the system. So in terms of methane, there's no significant difference across the three systems. Where we are getting reductions is clearly in the nitrous oxide emissions associated with the application of nitrogen fertilizer on the intensive system, with significant reductions being seen on the best practices systems, with lower and zero inputs of fertilizer nitrogen. And we also get a difference in terms of the overall carbon dioxide emissions associated with the three systems. There's a twofold reason for this. The first being that the carbon dioxide emissions associated with the production and transport of fertilizer nitrogen are much less on the best practices systems, being lowest obviously on the system that's applying minimal fertilizer nitrogen input. The second reason for the difference in carbon dioxide emissions is in terms of the emissions associated with the application of urea or protected urea fertilizers, which will be applicable to the best practices with nitrogen and the intensive conventional systems. So this is a similar graph that shows the total greenhouse gas emissions per hectare, but instead broken down by sources. So you can see, again, it's very clear to see that the main difference is coming from the emissions from fertilizer. This category here would take into account both the upstream emissions associated with the production and transport of fertilizer, as well as the nitrous oxide emissions associated with the application of fertilizer. Across enteric fermentation, manure storage and application, concentrate, or other sources of emissions, there was no significant differences across the three systems. So the second set of carbon footprint results I'm going to show you adopt the emissions factors for nitrous oxide on the right-hand side of the table here. So this includes the site-specific emissions factor calculated at Solohead for calcium ammonium nitrate fertilizer. So we can see what this does to the emissions per kilo fat protein corrected milk and per hectare is increase the emissions on the intensive conventional system due to that difference in the emissions factor for calcium ammonium nitrate, with the other two systems remaining largely unchanged. So this now represents using the site-specific emissions factor for CAN fertilizer, a 30% reduction in the carbon footprint per kilo of fat protein corrected milk and per hectare for the best practices without fertilizer nitrogen relative to the intensive system. So again, this graph is very similar to the previous one I showed, just showing that the differences is all coming from fertilizer nitrogen inputs between the three systems, with the blue bar having increased on the basis of the increased emissions factor for calcium ammonium nitrate. So to bring the greenhouse gas emissions and the carbon footprint part of the presentation to a conclusion, we've achieved between a 20 and 30% reduction in the carbon footprint per kilo of fat protein corrected milk and per hectare using the best practices to lower greenhouse gas emissions. And we've established firmly that the emissions coming from biologically fixed nitrogen has an emissions factor of 0. So the next part of the systems analysis is to look at the ammonia emissions from the three systems. So we had a very similar objective in terms of ammonia emissions, in terms of establishing an emissions factor to do with biologically fixed nitrogen from ammonia. To achieve this sub-objective of the project, we had a very similar plot trial in terms of the nitrous oxide experiment to determine emissions coming from biologically fixed nitrogen compared to the baseline level of emissions occurring at Solohead. So the three treatments were, again, a perennial ryegrass sward receiving no inputs of fertilizer nitrogen, a white clover sward receiving no inputs of fertilizer nitrogen, and a perennial ryegrass sward receiving 250 kilos of fertilizer nitrogen, with the point of difference here being that this fertilizer nitrogen type was in the form of urea. So the system of measurement in terms of how we measure the ammonia emissions from the systems is using the wind tunnels you can see on the right-hand side of the slide. So these wind tunnels are drawing air through the tunnels post-fertilizer nitrogen application for 3-week periods. They take a sample of air at the beginning and the end of the tunnel, capturing the ammonia in acid traps within the box here you can see in the photo. And the difference between the sample of air at the beginning and the end of the tunnel gives us the associated emissions within the area of the tunnel being generated. So the results over 2 periods of measurement for this experiment show that there was, again, no significant differences between the background level of emissions coming from the perennial ryegrass sward with no inputs of fertilizer compared to the emissions coming from biologically fixed nitrogen on the white clover plot. We can see that the plots that received annually 250 kilos of urea N per hectare had significantly higher proportion of ammonia losses on that treatment. So before we model the ammonia emissions the same way we did the carbon footprint emissions, we've established that the ammonia emissions factor for biologically fixed nitrogen, similar to the nitrous oxide one, is 0. And when we model the ammonia emissions for the 3 systems, we can see that the highest ammonia emissions per kilograms of ammonia per ton of fat protein corrected milk are 3.8 on the intensive conventional, dropping down by around 40% to 2.7 and 2.3 on the best practices systems, respectively. The ammonia kilos per hectare saw a similar magnitude of reduction in terms of a 37% reduction from 54.1 kilograms per hectare down to 34 kilos on the best practices without fertilizer nitrogen. So again, to establish the where the sources of emissions from each system are coming from in terms of ammonia emissions per kilogram of fat protein corrected milk, we can see a significant difference in the total ammonia emissions as I presented in the previous slide. There are 2 points of difference in terms of the ammonia emissions. The first one is clearly from the manure application. So we can see that the benefits of the low emission slurry spreading, giving a 60% mitigation on the ammonia emissions compared to slurry applied with the splash plate on the intensive conventional system, create a significant difference in the ammonia emissions from manure application. And as well as that, we're getting an obvious reduction in ammonia emissions from the application of fertilizer nitrogen across the 3 systems as well. So we've established that the best practices have reduced ammonia emissions by 40% compared to the intensive conventional systems, and that biologically fixed nitrogen has an ammonia emissions factor of 0 as well. So the final part of the systems analysis is to look at the economic performance of the 3 systems. So in a similar way to both the carbon and ammonia footprint modelings, we used an economic model to scale up the production data to represent a 50-hectare farm using average, variable and fixed costings at Solohead Research Farm from 2019 to 2021 as a baseline scenario for our economic analysis, using other sources such as the National Farm Survey and the CSO to obtain costings for the systems. We factored in full labour costs within the economic analysis at just under €18 per hour, 27 hours per cow based on work done at Teagasc Moor Park. Replacement heifers were contract reared within the economic analysis. And we also looked at 12 different scenarios covering 4 different milk prices and 3 fertilizer nitrogen prices to look at the sensitivity of the differences between the 3 systems to changing market prices. So the farm profiles for the 3 systems were as follows. As I said already, the land hectare was 50 hectares. The number of cows was the same as the carbon and ammonia modelling for the systems. The replacement rate was 18%, with the replacements contract reared as part of the economic analysis. The stocking rate was the same as the carbon and ammonia analysis. And just to note that there was a different rate of reseeding for the 3 systems reflected in the economic costs. So an average of 6% on the intensive conventional systems, with higher levels of reseeding at 9 and 12% respectively on the best practices systems to promote and obtain the level of clover content on these systems. So this was factored in at a cost of €1,100 per hectare in terms of reseeding costs. So when we scale up the economic performance at the baseline scenario, so that's using those average costings that's all ahead from 2019 to 2021, as well as milk price, the average milk price and average fertilizer nitrogen costs from that time period, we can see milk sales scaled up per farm are not significantly different in terms of kilograms of milk or kilograms of fat protein corrected milk per farm. This isn't surprising due to the same level of milk production across the 3 systems, as well as the similar stocking rates between the 3 systems over the course of the experiment. When we include the sale of calves and cull cows across the systems, there's no significant differences in total sales. But where we do see significant differences are in terms of the costings per farm. So within the variable costs, when you pull out the cost of fertilizer nitrogen, it's not surprising to see that there's a significant difference in the costings for fertilizer nitrogen across the 3 systems. And this is largely reflected within the variable costs. So you can see that despite the higher levels of reseeding on the best practices with fertilizer nitrogen and without fertilizer nitrogen, this is largely absorbed by the difference in costings to do with fertilizer nitrogen across the three systems. There was no differences in fixed costs down to the similarity in cow numbers and stocking rates of the three systems. And the difference we can see here in terms of the total costs is largely reflected in the variable costs of the three systems. So what this did in terms of the net margins and the profit per hectares of the three systems is give us a significant difference where we can see at the baseline level of analysis, the best practices with fertilizer nitrogen is significantly higher than the intensive control, with the best practices with fertilizer nitrogen being intermediate between the best practices without and the intensive conventional system. So the final part of the puzzle is to look at the sensitivity of the economic performance of the three systems to changing fertilizer nitrogen and milk prices. So to carry out the sensitivity analysis I referenced earlier. So to do this, we looked at a range of fertilizer nitrogen prices from 2004 to 2023. And we picked an intermediate fertilizer nitrogen price of €1.05 per kilo of nitrogen, a low fertilizer nitrogen price of 85 cents per kilo, and a high fertilizer nitrogen price scenario of €1.35 per kilo. So these are taken from 2015 onwards, representative of the general upward trend in the costings of fertilizer nitrogen over the last number of years in Ireland. We did a very similar exercise for the base milk price. So you can see again, there's a general upward trend in terms of milk price base milk price received in Ireland over the last number of years. We know that 2022 and 2023 had higher milk price, had relatively high milk price years. So we chose a low milk price of 27 cents per litre, which was reflective of prices in 2016. We then increased in increments of 6 cents per litre to an intermediate price of 33 cents per litre, a high price of 39 cents per litre, and a fourth milk price representative of the average of the last 3 years at 45 cents per litre. So there's a lot going on within this graph, but I suppose the first thing to note is that the sensitivity of the net margins to milk price across the three systems was very high. So as we increased the milk price along the bottom of the graph here, we can see that it had a significant effect on the net margins of the systems. But probably more importantly in the context of the overall study, and it's notated by the significance level here with no significance, a 1-star level of significance and a 2-star level of significance occurring within the different nitrogen fertilizer prices used within the three systems. So the sensitivity of the differences between the systems at a low fertilizer nitrogen price showed that there was no significant differences at low fertilizer nitrogen prices between the three systems. However, as we move to scenarios of medium and high fertilizer nitrogen prices, we can see that there was a difference between the best practices without fertilizer nitrogen compared to the intensively fertilized system, with the intensive system being intermediate. And when we move to a high level of fertilizer nitrogen prices, high fertilizer nitrogen price scenario, both the best practices without fertilizer nitrogen and with fertilizer nitrogen were significantly higher compared to the intensive conventional system. So I suppose what this is saying is that the differences between the systems are sensitive to fertilizer nitrogen price, but because the trend of significance was repeated across each milk price, the differences between the systems were not overly sensitive to changing milk price. So that brings me towards the end of the overall systems analysis and towards the end of the presentation. I suppose the conclusions I would hope people would have taken from the presentation is that using best practice approaches, we've reduced greenhouse gas emissions by between 21 and 30%, depending on the emissions factor used within the life cycle assessment analysis. We've reduced ammonia emissions by 39%. We've established that nitrogen fixed by clover in grass clover mixtures has an emissions factor of 0. We've maintained profitability or improved profitability using the best practices depending on fertilizer nitrogen price. And greenhouse gas emissions were primarily lowered by displacing fertilizer N with fixed N for associated with clover. And low emission slurry spreading protected urea and eliminating fertilizer N were most effective in reducing ammonia emissions across the three systems. So just before I finish, I'd like to acknowledge the project funding from the Department of Agriculture, Food and the Marine, and to acknowledge my supervisors, Dr. James Humphreys and Imelda Casey, and the other colleagues within the project as well. So, Mark, that brings me to a close, and I just like to say thank you very much and looking forward to the questions
Thank
now.
you, Owen. Really excellent presentation. And whilst you went through a lot of detail, I think you brought us through it very um, step-by-step manner, which is not always easy. So just could you remind us about the difference? Because I know as it went through the presentation, you did talk about the difference between the intensive system, intensive conventional, the best practice and then the best practice zero. Just to remind us what the key differences were, particularly between the intensive conventional and the others.
So the intensive conventional system was supposed to be representative of commercial practices on intensive commercial dairy farms over the last decade or even previous to that. So that involved applications of fertilizer nitrogen at the time of between 250 and 280 kilos per hectare on that system. This was applied using unprotected urea and calcium ammonium nitrate,
Mhm.
which would have been reflective of practices previously on dairy farms. And this system had the lowest clover content at 10%, and slurry application was conventional in the form of the splash plate.
Mm.
So the best practices with fertilizer nitrogen then is a system that Solohead has run for many years and has quite an extensive data set on, and it's a system receiving um, reduced fertilizer nitrogen inputs applied in the spring only, so allowing clover to fix nitrogen for the remainder of the season to achieve herbage production growth. This system would have traditionally had urea as that fertilizer nitrogen source, with protected urea being adopted later in the study from 2017 onwards to lower the nitrous oxide emission, the ammonia emissions associated with the application of unprotected urea. The clover contents on this system were higher at 23%, and low emission slurry application was adopted in the form of the trailing shoe. So then just to take it a step further to, I suppose, lower emissions as far as was possible within the context of Solohead, there was the elimination of regular fertilizer nitrogen application to the systems on the best practices without fertilizer nitrogen, with just the exception of the fertilizer nitrogen being applied to reseeded swards, which represents a very small amount of fertilizer applied on the overall system basis,
Okay, no, that's thanks for
if that
reminding
makes
us of
sense.
that because it's yeah, no, total sense. Yeah, that makes a lot of sense. In terms of the risks associated with the different systems, have you taken a look at that? Obviously, there's increased management required with clover swards and so on. I mean, have you looked at those dimensions, that other input that's required? Because of course we're looking at the labor that's associated with a lot of these systems, and I know that mightn't be specifically part of your study, but have you any comments on that?
Yeah, like it's an interesting point. I suppose the barriers to the adoption of these systems from our point of view and from the point of view is why is there not more clover on farm level is probably the competitiveness of the economics of a conventional system. The reality is, despite we've maintained profitability across the systems, but as you say, when the management is much simpler to go out and spread your fertilizer to grow your grass, when there's no huge economic incentive to adopt clover, we can see that the adoption across the country has probably struggled in terms of adopting these sort of systems. In terms of the overall management between the systems, there's kind of the difference in management would probably be mitigation of things like bloat on the clover systems, which the team at Solohead have had a number of cases of bloat. But I suppose the extra costs in terms of bloat oil that has been used at Solohead were included to some extent, and the other mitigation practices, but the labour costs we didn't associate it being different within the context of the study for the moment. But there's no doubt about it. There is, I suppose, an increased level of management required within these clover systems.
Mm. But I mean, at the same time, the reductions that you're achieving there are pretty astonishing. A 23% reduction in greenhouse gas emissions, and then almost 40% reduction in ammonia. I mean, that is something that we really, as a country, have to be striving for. So I think definitely there's a lot of lessons to be learned there from Solohead. Meabh, a few interesting questions coming through, and I know you have a few of your own up your sleeve as well that you're keen to put to Owen.
I do. The list has been growing here as the presentation went on. So, yeah, look at a couple of interesting questions coming in. I suppose in terms of the comparison on between the BPN scenario, so your best practice with chemical N versus your best practice with zero N. Was there any other difference in the management practices between those two systems other than just the chemical nitrogen application levels? Was there any other differences between those two systems?
So as such, no. The systems were managed the same in terms of grazing management practices, in terms of the adoption of clover, and day-to-day management practices. They're not managed overly differently, aside from that nitrogen being applied in the spring on the best practices with fertilizer nitrogen. All the systems got the same treatment in terms of the proportion of slurry applied and things like that. So no will be the simple answer there.
Perfect. So it is just isolated, I suppose, to that change in the chemical nitrogen level that's going out.
Yeah.
Perfect. Another question there as well, in terms of, I suppose, looking at the general scenario then versus the best practice scenario and the clover inclusion level there. Do you know, if there is a farmer that's maybe operating at that 10% clover inclusion rate, and they want to maybe take that step to get it up closer to the 23% that you were showing, you know, what steps would you have, what recommendations would you have for them to help them achieve that?
So I suppose if you're starting from a system akin to the conventional practices systems, and you have 10% clover within swards, the reality is that's probably not enough to deliver the levels of fixation required to achieve the herbage production growth we've seen at Solohead. And we know from extensive research within Solohead, the best way to achieving clover within swards is a level of full reseeding. So a full reseeding program. So if you're starting with very low levels of clover on farm, to get to a stage where you're at 100% clover coverage of between 23 and 30% clover content within swards, you're probably looking at between a 6 and 8 year process using a combination of primarily reseeding, an intensive reseeding program, with a combination of a small level of oversowing, which we'd be less reliant on, especially in terms of establishment. Full reseeding would be the practices to use. And secondary to that, to come back to the question, the slide there that showed the correlation between the levels of fixation and the application of fertilizer nitrogen within the year of reseeding, that's how farmers that have, I suppose, had discussions with us have built confidence in the system, is not applying any further chemical nitrogen to those reseeded swards, to see in the first year that you can achieve that level of herbage production once you get your clover established well, without the levels of chemical fertilizer nitrogen input.
I do think that maybe is a bit of a barrier for people, is just that level of confidence in it, you know, to take. It is a big leap, I suppose, to take, to have confidence in the sward to be able to do that. So just another question there as well, in terms of like the how big a proportion of the carbon footprint was being made up from the chemical fertilizer and stuff. I suppose it might just be worth talking about the LCA, you know, your life cycle assessment versus maybe the IPCC method, and how that can change how the carbon footprint maybe appears.
Yeah, so like I presented both results because I suppose for comparability purposes, the national inventory method, which is the framework developed by Mary Harty and Patrick Forrestal, with that 1.5% emissions factor to do with calcium ammonium nitrate, that's what's used in the national inventory at the moment in terms of emissions from calcium ammonium nitrate. We know that there's significant reductions in nitrous oxide emissions when you switch to protected urea. So within the context of using the site-specific emissions factor for calcium ammonium nitrate measured at Solohead, I suppose it increases the accuracy of the measurements that we have available to us at Solohead. And I suppose it reaffirms the point that moving away from calcium ammonium nitrate and replacing it with either protected urea, or in Solohead's context, biologically fixed nitrogen, is allowing us to achieve significant emissions reductions, regardless of what emissions factor you use. So going forward, I suppose there's a probability that we move from the tier 2 emissions factors that we have in terms of the 1.5% towards more regional or even soil specific emissions factors, which in Solohead's case is higher than is currently used in the national inventory. But that might not be the case across all soil types.
So a question, and I'm going to maybe bring you in on this one as well, Meabh, in terms of the adoption of these types of systems. And you've touched on it there, that the challenges faced by farmers, or that weaning process from high nitrogen systems. Like Meabh, on the ground, what are you finding there? Are the kind of the views of farmers around this?
Yeah, I think there's a bit of a variation, maybe depending on the level of experience. Owen talked about the importance of management around clover and stuff. So I think I think it takes a little bit of time. The farmers who've maybe been incorporating clover over a longer period of time have maybe gotten more used to the management around it. But then I suppose it's something that we're encouraging among more and more farmers. So the ones that are maybe newer to it, it does take that little bit of time to take the leap, even to start cutting back during the summer months and stuff. So I suppose something that we're recommending is, split the paddocks and compare, cut back on one and don't cut back on the other, and let, the proof is in the pudding for them to be able to see that. So that's kind of what I've been seeing on the ground, but it's just taken a little bit of time, I think, to build that confidence around the management decisions.
Mm -hmm. And Owen, from your own perspective, what do you think can be done to support that adoption on farm?
Like, I think if we're starting from a very low baseline level in terms of clover on farm, the best way to achieve confidence in it is a full reseed. And then within the context of that year, you can afford to pull back the nitrogen, and that gives you the confidence to continue on. And if you get 1 year done and you're happy with it, it gives you confidence to build on that. Like the work at Solohead is there to bridge the gap, but I suppose until we get commercial flag farms, achieving the same results, which there are. There's a group working with Solohead, achieving very good results in this regard, and they all started with just building confidence from good reseeds. Really is the key, I think, if you're starting from zero.
Yeah, and I know even on some of the Signpost demonstration farms as well, they've achieved a brilliant level of reductions in their chemical nitrogen applications as well through their clover management.
Yeah,
and
that's that's reflective in nitrogen reduction levels on farm. We've seen it come down there over the last number of years now. There's a price element to that as well with high prices, but there's definitely strides being made at farm level.
Yes, and there is a question there then, just in terms of clover establishment on wetter ground, and maybe issues around that. Would you have any advice on that, or any experience in terms of getting that good establishment on wetter areas?
So, like Solohead would be considered a heavy enough soil. There's been a nice bit of drainage work done to aid with that at Solohead. So, I suppose the first thing I'd say is that if you have a method of drainage that could be applicable to a soil type to help aid in your drainage problem, that's probably the first place to start. But in terms of establishing clover, it's a case of a spring reseed, with good clover varieties. We know the recommendations for reseeds in terms of grazing over the first couple of rounds. There's no real difference in clover reseeds between grass only reseeds in that regard. But soil type as such doesn't really have an effect on how you'd manage a clover reseed. What probably affects clover in terms of heavy soils is if you're having to close up very early in the autumn and not getting out until very late in the spring, and you have a large overwintering period where there's not light getting to the base of the sward. That can probably be a challenge for wetter farms. So that's probably the biggest risk I would see in terms of soil type for clover. But there's lots of management practices around that in terms of on-off grazing to achieve optimum light to the base of the swards for clover swards in those soil types.
And there's a lot of like with today we're talking about greenhouse gas emissions and ammonia, and not everyone is aware that we do have very tight targets in relation to reducing our ammonia emissions as well. It's not something that's talked about as often. There's the Gothenburg Agreement that has very much stipulations there for Ireland. But just in terms of water quality, you know, there obviously are significant benefits from that perspective that we haven't really discussed today, and I know wasn't part of maybe your remit, but maybe would you care to comment on that?
Yeah, so like the nitrate end leaching to groundwater in Solohead has been measured over a 20-year period intermittently, and I've did some recent measurements myself, which I didn't present today in the presentation, but the average nitrate N concentration at Solohead to groundwater is 2.24 milligrams of nitrate N per liter, which is very low levels of nitrate N leaching with virtually no differences between a sward receiving fertilizer N or a sward with clover. So really, clover isn't putting us up or down in terms of nitrate N leaching at Solohead, but the reality is the farm is leaching low levels, and a large part of that is down to the soil profile of Solohead. We can see that we're losing more emissions in terms of nitrous oxide N in gaseous form, and that's really the main pathway for losses at Solohead down to the soil type.
Yeah, so it would be interesting to see the same, I suppose, to see the results from the same trial carried out maybe on a more freely draining soil, and that would be riskier maybe for that nitrate loss. Yeah.
Yeah. But I suppose the mechanization of fixation is kind of in what you describe as when you have conditions for fixation, you have conditions for growth because you need high soil temperature, you need oxygenated soil for the rhizobia bacteria to fix that nitrogen. So there'd be conditions conducive of, I suppose, not leaching nitrogen, but we would need a more robust data set in terms of the effect of leaching. But from Solohead's perspective, adopting clover doesn't put you up or down in terms of losses of nitrate into water. The biggest risks will be overground runoff in terms of dung and urine deposits or slurry application, and you can mitigate around that by best practices in terms of slurry applications. So
Perfect. And then just coming back to the I suppose your pea management on the farm there as well. There's questions coming in terms of farms with little to no pea allowance for the year, and how you would manage clover establishment around that.
So in terms of pea, there's no allowance at Solohead for pea as it's an index 4 soil. It's index 4 for K as well. We'd probably establish that, and there's a PhD student, Tom McCarthy, working on the importance of K fertilization in the context of grassland production and clover swards. But regardless of soil type, there have been routine applications of K used at Solohead to promote the levels of fixation being achieved on the farm, with the idea being that it's important for, I suppose, root structure and development, with the root structure of clover being quite shallow. So keeping that level of K at the surface of the soil, regardless of your soil indices, in roughly about 15 kilos every second round during the main grazing season. So roughly around 60 kilos per hectare applied as fertilizer K would have been applied on the best practices systems at Solohead to promote fixation. So we've no allowance for peas, so it's going on in usually the form of muriate of potash. But I suppose if you have an allowance for pea on your farm, the recommendation might be to spread half a bag of 0.730 maybe every second round to aid your clover swards in terms of fixation.
And Owen,
just sorry,
go
Mark.
ahead, Meabh.
Yeah, sorry, just sticking with soil fertility, I suppose, just a quick word on the importance of pH and where the pH levels are at maybe in Solohead as well.
Yeah, so I suppose in the context of trying to optimize biological nitrogen fixation, so the key word there is biological. So biological processes usually function optimally at a neutral pH. So while the advice for normal grassland would usually be around 6.3 for pH, Solohead has around a pH of around 6.6, with some paddocks closer to 7. So we'd be happy to recommend getting to a pH of closer to the 6.5 and upwards for soils. Now I know that can be difficult for some soil types depending on locking molybdenum concentrations and locking up copper and that sort of thing. But to optimize fixation, having close to a neutral pH is actually more optimum.
And Owen, just in relation to, we talked a lot about the more on the grazing side of things there, but in terms of the forage production there in Solohead, what sort of are you using any red clover type species, or is it just
So
using the
so from 2019 onwards, the standard grazing mixes used on the best practices systems there would have included 2 kilos of white clover and 2 kilos of red clover as well within the grazing mixes.
Mhm.
The idea of that is that the red clover seed, number one, is faster establishment. It's a bigger seed size, and can, I suppose, contribute to high levels of fixation within particularly the first couple of years post reseeding. This allows, I suppose, the higher levels of fixation, and the idea would be that that would die out of the sward over time, but having served its purpose, and the white clover is still the basis and the main engine in terms of delivering high levels of biologically fixed nitrogen to the sward. But I suppose what we're seeing is that after almost 5 to 6 years of that level of red clover sward inclusion on the grazing mixes, there's still a level of red clover within the sward, which is surprising in itself. So it's probably one of the things that came out. There is silage outblocks that weren't applicable to the studies that I presented in this presentation that do have specific red clover silage mixes as well in Solohead, but maybe that's probably outside my remit for today, maybe.
Okay, just following up on the clover one there, we had a question in relation to the kind of the fixation behavior of clover, particularly in a new reseed. Have we any information on how quickly that fixation kicks in?
So my understanding of fixation from the literature and from the herbage production we've seen from newly reseeded swards at Solohead, and as well from physically digging up the clover swards, is that we have to remember in terms of the mechanics of fixation, what's fixing the nitrogen is rhizobia bacteria, which contain these enzymes that can cut the triple bond of nitrogen in the air into the soil, which can then be taken up by forage plants. What the clover does is create the housing unit for these bacteria. So as soon as you have nodulation, which is the housing unit for the bacteria, by default you essentially have fixation because the clover plant is providing energy through photosynthesis to the rhizobia, which is then fixing the nitrogen and delivering it to the soil. In terms of delivering that nitrogen to the grass plant, there's probably three ways where that happens. Usually it's in the form of stolon degeneration post grazing, where once you have grazing, you have a level of root mass that decays, which then releases that nitrogen, which can be taken up by the grass plant, or it can be directly transferred as well. So as such, one of the main motivations for not spreading any fertilizer nitrogen on your reseeds is the fact that you are getting levels of fixation within the first year. And I think that's well established within international literature as well as the research at Solohead. The other point to make on that is that when you cultivate your soil and there's usually a level of manure incorporation into your reseed, you're flushing that reseed with a level of nitrogen that supports a high level of growth anyway, and in terms of sward establishment. So within the context of this study, there was some level of fertilizer application to aid sward establishment on reseeds, but that's now been removed, and they've been trying it without it on the latest reseeds done at Solohead. So, yeah,
Okay.
essentially we're getting it within the first year, to answer the question.
We've time for one final question, Meabh, if you want to squeeze it in.
I think I'm going to be very selfish and ask a question for myself. Going out as, as a climate action and sustainability advisor, I suppose, and looking at maybe some of the measures that were included in the conventional intensive system there, I suppose in the last few years, we've seen a big move away from splash plates. A huge amount of farmers have adopted dribble bars, low emission slurry spread, and a lot of them are using protected urea now as well and stuff like that. So for a farmer who's maybe already started taking the first few steps on their journey, like what would be your main recommendations for those farmers? How would you tell them, I suppose, to approach the next step in their journey to maybe reducing chemical nitrogen, reducing their emissions?
So I suppose it comes down to what the farmer is willing to do in terms of their own management practices and what they're comfortable with. I suppose the objectives of this study were to show what's possible when you take the best practices that we have to their probably most, for want of a better word, extreme level. So if a farmer is willing to go to zero nitrogen across their farm, there's clear guidelines and from the framework carried out within this study to achieve that. Within the context of your own emissions profile on the farm, we know we're getting life cycle assessment results with the AgNav project there. So it's a case of looking at your level of fertilizer nitrogen input, looking at where you can probably reduce that in terms of your clover contents, and increasing your clover proportion within the farm is probably the real next step, because the reality is there isn't a lot of farms at the level of Solohead would be at in terms of being able to achieve the fertilizer nitrogen reduction without impacting on their herbage quality. So it takes time.
Okay, we're going to have to leave it at that, Owen. We're right out of time, but obviously a huge interest in the work that you're doing, and congratulations on the excellent data that you've developed, and best of luck with the rest of your studies over the next.
Thank you very much.
You're nearly there by the sounds of it, anyway. So not too far to go. Meabh, thanks a million for the questions and your own questions as well. Really important to get that as a perspective from on the ground, and how it's actually being rolled out with farmers. Just to let you know that next week we are going to be joined by Dr. James Humphreys, who is the Principal Research Officer at Solohead Farm. And James is going to be talking about the wider context of the low-cam dairy project. So do join us for that next Friday. My thanks to Mary O'Loughlin in the background today helping us, and Yvonne Maher and Pat Murphy on our wider team. And we look forward to seeing you next week. Until then, stay safe.